Imagine a spacecraft so advanced it can travel to space, accomplish its mission, and then return to Earth only to be used again. SpaceX has turned science fiction into reality with its groundbreaking Starship Booster recovery system. But this innovation hasn't just made headlines, it has sparked a heated conversation in the space community, even putting NASA scientists in an awkward spotlight. So, how exactly does SpaceX recover its Starship Booster, and why does it outshine NASA's current methods? Let's dive in to uncover the fascinating details. If you've been following SpaceX for a while, you've likely noticed how the company consistently pushes the boundaries of rocket recovery technology. From landing boosters on drone ships to catching them with a tower, SpaceX has redefined what's possible in the aerospace industry. For decades, the reality of space exploration was grim when it came to rocket reusability. Rockets were either partially destroyed after launch or lost entirely, creating immense waste. This inefficiency stood in stark contrast to humanity's dream of exploring the universe. Enter SpaceX. The company revolutionized the game by developing groundbreaking methods to recover and reuse rockets. By challenging conventional norms, SpaceX has not only shattered long-standing barriers, but also reimagined how we manufacture and launch spacecraft. Take the Falcon rocket series, for example. This line of rockets has been at the heart of SpaceX's recovery success. Since achieving its first successful Falcon 9 landing in December 2015, SpaceX has recovered approximately 376 rocket boosters and reused them in 352 launches. This incredible feat hasn't just made spaceflight more practical, it's made it far more cost-effective. Of course, some may point out that NASA also recovered and refurbished solid rocket boosters during the Space Shuttle era. While true, a closer look reveals significant differences in cost and efficiency. The entire shuttle program cost $192 billion by 2010, averaging $1.4 billion per mission across 134 flights. In stark contrast, a Falcon Heavy launch, a rocket with double the payload capacity, comes in at just $150 million per mission. This comparison highlights a key point. While NASA's shuttle program was a historic milestone, it wasn't optimized for cost. SpaceX, on the other hand, has achieved both technical brilliance and economic efficiency, setting a new benchmark for space exploration. The Space Shuttle was a remarkable feat of engineering, but its reusability had its limits. While the large orange fuel tank was the only part of the shuttle that wasn't reusable, recovering and refurbishing the other components was a complex and costly endeavor. Each orbiter underwent extensive refurbishment between missions. Technicians performed detailed inspections and replaced critical components as necessary. One of the most demanding tasks was maintaining the shuttle's thermal protection system. Each individual heat shield tile, vital for safeguarding the spacecraft during re-entry, had to be carefully examined and replaced if damaged. The solid rocket boosters, SERBs, presented another challenge. Designed to be reusable, their recovery process was far from cost-effective. After launch, the SERBs parachuted into the ocean, where they were retrieved, cleaned, and inspected. This involved a time-intensive cycle of disassembly, testing, and reassembly. Despite the intent to save money, the labor and material costs of refurbishing SERBs often exceeded the cost of manufacturing new ones. This harsh reality contradicted the original vision of dramatically reducing launch expenses, contributing to the shuttle program's high overall cost. SpaceX revolutionized rocket reusability by introducing the concept of vertical takeoff and landing for its boosters. But the company didn't stop at making rockets reusable. They also focused on making them quickly reusable and cost-effective. This approach marked a dramatic shift from the practices seen during the Space Shuttle era. The latest Falcon 9 iterations have significantly reduced the need for lengthy refurbishments. The average turnaround time for a Falcon 9 booster has been slashed from 356 days to just 107 days, with the current fastest turnaround at an impressive 21 days. Although SpaceX doesn't necessarily prioritize ultra-fast turnaround times For Falcon 9, due to its robust fleet of boosters stationed across the country, the company's ultimate goal is to achieve a refurbishment period of just 24 hours. How? By adopting a process akin to commercial airliners, where rockets would require only a swift inspection between flights. During the short refurbishment period, the Falcon 9's first stage undergoes meticulous maintenance and inspections to ensure peak performance for its next mission. Once the booster returns to Earth, whether by road or sea, it's transported to one of SpaceX's dedicated refurbishment hangars. These facilities are equipped to handle multiple boosters, enabling the company to maintain its impressive launch cadence while refining its turnaround processes. SpaceX's focus on speed, efficiency, and innovation continues to set a new standard for spaceflight, proving that reusability is not just about recovery, but about transforming how we think about the economics and logistics of space exploration. Between Falcon 9 launches, SpaceX carries out detailed operations to ensure its boosters are ready for their next mission. One key component under scrutiny is the landing legs. These legs, which bear the brunt of impact during landings, are often some of the most frequently refurbished parts of the rocket. While they're typically folded before the booster is placed on a transport vehicle, SpaceX has faced challenges in the past, occasionally requiring the landing legs to be manually removed for maintenance. Once the booster is transported to the hangar, the refurbishment process kicks into high gear. Each Merlin engine undergoes rigorous testing to confirm it's flight ready. According to Elon Musk, a Merlin engine can handle up to 1,000 flights without requiring significant refurbishment. Beyond longevity, these tests allow engineers to study engines that have flown multiple missions, pinpointing which parts wear out the fastest, a crucial factor in making Falcon 9 the most reliable rocket in the world. The hydraulic grid fin system, used for precision steering during descent, is another area of focus. It's inspected thoroughly for potential hydraulic leaks. Fuel tanks and pressurized vessels also go through advanced ultrasonic testing to detect microcracks that could lead to failures under the intense pressure of flight. One of the biggest variables SpaceX monitors is the pressure cycle data gathered from every Falcon 9 mission. Each launch adds to a growing library of insights, helping engineers refine the design and maintenance of these rockets, ensuring they remain both safe and efficient for future missions. This meticulous process highlights SpaceX's commitment to continuous improvement and innovation in spaceflight technology. After a booster passes its thorough inspection process, it undergoes a critical static fire test where all 9 engines are fired to confirm performance. Once it clears this step, the booster is attached to the second stage and payload, ready for its next mission. These meticulous checks are essential, especially as SpaceX pushes the boundaries of multiple reusability. Each mission offers valuable data, helping the team refine the refurbishment process and better understand how many flights each booster can handle. Looking ahead, SpaceX continues to innovate, with new milestones in sight for the Falcon 9 and beyond. But Falcon 9 is just one chapter in the company's groundbreaking journey. SpaceX's evolving rocket technology has paved the way for revolutionary recovery methods with unprecedented turnaround efficiency. A prime example of this is their plan to catch rockets using the launch tower. Unlike Falcon 9's autonomous landing system, SpaceX has developed the chopstick arms on the launch tower to catch Starship rockets. This bold approach was demonstrated during the Starship Flight 5 launch in October, showcasing the next leap in rocket recovery. During a tower catch, the rocket approaches the launch site, carefully aligns with the gap between the outstretched chopstick arms, and hovers in place before being gently secured. This innovative method highlights SpaceX's commitment to rethinking the limits of reusability, setting the stage for even faster turnaround times and more ambitious missions in the future. SpaceX's innovative chopstick arms offer a groundbreaking approach to rocket recovery, eventually catching boosters and starships as they gently come to rest on hard points, each about the size of a coffee table. These arms act as small, fixed landing platforms with the ability to make minor positional adjustments in real time. This design could significantly streamline post-recovery operations by eliminating the need for cranes or other equipment to lift and secure landed boosters or spacecraft. By contrast, Falcon 9 rockets rely on 3 to 4 deployable landing legs to touch down on drone ships. While effective, this system introduces logistical challenges. Once a Falcon 9 booster lands, it must be transported to a refurbishment hangar where components, including the landing legs, undergo extensive maintenance. These legs are critical, but time-consuming to inspect and repair, adding complexity to the refurbishment process. This is where SpaceX's experience with Falcon 9 landings has been invaluable. They've learned that simplifying recovery systems can lead to faster turnaround times and greater efficiency. For the massive, super heavy removing landing legs entirely represents a game-changing decision. Without the extra weight of 6 legs, Super Heavy can dedicate more of its payload capacity to cargo or fuel, increasing its overall performance. This minimalist approach not only saves valuable time, but also aligns with SpaceX's ultimate goal of rapid, cost-effective reusability, setting the stage for the next era of space exploration. The landing apparatus for SpaceX's rockets makes up roughly 10% of the entire booster's weight, highlighting the innovative yet complex nature of their rocket catching system. While undeniably unique, this method poses significant engineering challenges, leading many space enthusiasts to ask, why doesn't SpaceX design rockets to be simpler, like space planes that take off and land horizontally? The answer lies in the fundamental differences between rockets and aircraft. A spacecraft designed like an airplane has significant disadvantages compared to a vertically launched rocket. One key factor is drag. Spaceplanes spend more time traveling through the atmosphere, increasing resistance and fuel consumption. Rockets, on the other hand, minimize this by launching straight up, quickly escaping the densest part of the atmosphere before turning to travel sideways. Additionally, spaceplanes require complex propulsion systems, such as jet engines or air-breathing rockets, to counteract the energy losses caused by drag. Developing these engines is far more expensive than building traditional rocket engines. Unlike jet engines, rocket engines don't need to be designed to intake air efficiently at varying speeds from subsonic to hypersonic. This simplicity makes rocket engines more cost-effective and reliable. By focusing on vertical launches and landings, SpaceX can maximize efficiency, reduce costs, and achieve reusability on a scale that horizontal takeoff and landing systems simply cannot match. This approach underscores why rockets, despite their complexity, remain the superior choice for reaching and returning from space. Rocket engines are designed for a single environment space, making them much simpler than the engines required for air-breathing spaceplanes. Re-entry, however, is where the differences between rockets and planes become even more apparent. Spaceplanes face significant challenges during re-entry. They must travel through hypersonic, supersonic, transonic, and subsonic speeds, all while enduring extreme heating from atmospheric friction. This complexity forces engineers to make design compromises. Take the Space Shuttle Orbiter, for example. It needed large, heavy delta wings to handle varying airspeeds, thousands of heat-resistant tiles that required frequent replacement, and a massive tail fin to maintain yaw control as it navigated through the atmosphere. Rockets, like SpaceX's Falcon 9, bypass most of these issues. The Falcon 9 slows down before re-entry, free falls through the atmosphere, and relies on precise landing burns to touch down safely. By avoiding the need for wings and other aerodynamic structures, rockets streamline the re-entry process. Additionally, rocket bodies are inherently simpler than planes. While planes require a carefully shaped fuselage to minimize drag and generate lift, a rocket is essentially a sturdy, cylindrical fuel tank with engines attached. Roll a strong aluminum alloy into a tube, insert propellant tanks and engines, and you've got the foundation of a rocket. In short, each vehicle is purpose-built for its environment. Planes excel at flying within the atmosphere, while rockets are optimized to break free of it. Trying to make a perfect rocket that flies like a plane, or vice versa, is like asking a fish to climb a tree. Both are best suited to their natural habitats. If you try to make a rocket fly like a plane, you'll end up with so many compromises that it essentially becomes a plane. And if you attempt to design a plane for spaceflight, it's likely to evolve into an overly complicated rocket. SpaceX's Starship Booster recovery begins with the Falcon Heavy's big brother, the Starship Super Heavy Booster. After lifting the Starship into orbit, the Super Heavy Booster disengages and begins its dramatic return to Earth. Guided by a suite of advanced technology, including grid fins for steering and cold gas thrusters for precise adjustments, it heads back to a designated landing zone. The real magic happens during its descent. Unlike traditional methods that rely on expendable rockets, the booster performs a controlled landing. Using multiple Raptor engines, it executes a boost back burn to position itself and a landing burn for a smooth touchdown. This reusability is revolutionary, allowing SpaceX to drastically cut costs and turnaround time. Compare this to NASA's traditional approach of disposable boosters, and it's easy to see why SpaceX has the upper hand. NASA's Space Launch System, SLS, is a technological marvel in its own right, but it comes with significant limitations. The SLS uses solid rocket boosters that are jettisoned into the ocean after their fuel is spent. While they are sometimes retrieved and refurbished, the process is costly, labor-intensive, and doesn't come close to SpaceX's efficiency. By contrast, the Starship booster can be ready for another flight within weeks, sometimes even days. This agility gives SpaceX a competitive edge in mission frequency and cost. NASA's SLS, although powerful, has been criticized for its astronomical budget and lack of reusability. With the Starship program, SpaceX is setting a new benchmark in space exploration, showing the world that there's a more economical way to reach the stars. The technological superiority of SpaceX's recovery system is no accident. It stems from years of innovation and a willingness to take risks. The Raptor engines, the backbone of the Starship system, are powered costs around $2 billion per launch. In contrast, SpaceX's reusability model slashes costs by up to 70%. By recovering and reusing the boosters, SpaceX makes space exploration more accessible, not just for governments, but also for private entities. This affordability is a game changer, opening doors to projects that were once deemed too expensive. The comparison with NASA highlights a shift in priorities. SpaceX is about making space travel practical, while NASA remains tethered to its legacy systems. SpaceX's innovations are reshaping the space industry. Their approach is not just about beating NASA, it's about paving the way for humanity's future in space. With the ability to reuse boosters, SpaceX is setting a precedent for sustainable exploration, reducing waste, and maximizing resources. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.